I'm going to talk to you today about iPhone, which isn't your guys' product, but hopefully some of the lessons learned will translate for you guys. So talk about fuzzing, how I find bugs, and then I'll go into a bug I found and how I exploited it. And then a little bit at the end, if I have time, about payloads on mobile phones. So what code can they get running on your phone if they can find a bug and exploit it. Okay, so who am I? I work for a company called Independent Security Evaluators. It's a consulting company from Baltimore. My claim to fame is I was the first one to hack an iPhone and the G1 phone as well when it came out. So that phone, the G1 phone, I actually hacked the day it came out because I found some T-Mobile employee who was selling his on eBay. So I got it like 3 days early, so that's pretty cool. I was very suspicious the guy was trying to rip me off the whole time. I was like, how do I know that this is really a G1 phone? And that's how I found it. He's like, oh, I work for T-Mobile. I was like, okay, I'll buy it. So it's good. I still have that phone. And then so I was also the first to hack Second Life, so that's fun if you ever Google it. It's like I could take over someone's little avatar and make them run around and do stuff. And then I won this Pono contest last 2 years, and I've written some books. So check them out if you want. So this talk, I gave 2 talks at BlueHat this year. So this is one about SMS and fuzzing and one about payloads. This is basically both of those talks smashed into actually 55 minutes, so you're going to miss out on a lot. If you want more details, check it out. It's all online. So the 2 talks were fuzzing the phone in your phone, which I did with Colin Wolner, who's he's like a postdoc in Germany, and post-exploitation bliss interpreter for iPhone with Vincenzo Iozzo, who's a student in a technical school in Milan. Okay, so what am I talking about? Basically the iPhone stuff, SMS, which you've already heard a bunch of from Zane and Luis today, so I'm not going to talk too much about that. Sully, which is a fuzzing framework, how I get SMS messages, how I do the testing. Most of the talk is going to be how I actually exploit it, because that's the thing that no one else really talks about. And then at the end I'll talk about, for the older version of iPhone, how you could do code injection, which is like actually get shellcode running, and then how you could leverage that to get Meterpreter, which is this other thing running too. All right, so this is the one slide I added after I turned in my slides because I was afraid they wouldn't let me say it. But here is my letter from the research community to you guys. Stop rebooting my machine when I have IDAPRO open. It ruins my databases. So don't do that anymore. I can't tell you how many times that's happened. It never tries to reboot during the day. It's only when I'm asleep. All right, so iPhone. First, so how is iPhone set up? What's their security model? So basically they did a few things to try to make iPhone hard to break into. One is they stripped out a lot of code. So it's basically OS X, like my computer, but they took off a lot of stuff. So they took off, for example, binsh. So there's no shell on the phone. So you can't have shellcode that just execs binsh because there is no sh. And even if you could get sh on there, like a shell, then there's no ls, no ps, nothing like that. So there's nothing good on there to do. And then furthermore, even though like Safari will handle 100 different file formats, mobile Safari will only do like 4 formats. So there's just less code to find bugs in. Like I said, talking about stripped on OS. The other thing they do is code signing. So you can't just download a binary onto the phone and run it. It has to be signed by Apple. So do they do memory randomization? No. So they didn't do any memory randomization, but really no one in the mobile space does that because I don't know why. I guess it takes up too much. The people at Android have said it takes up too much processing, but no one does it. Neither does iPhone. So sandboxing. So when you download a program from the App Store, it runs in a restricted sandbox. So the theory is even if someone can break into this process, no one cares because it can't do anything. Like it can't dial the phone. I don't think, at least. It can't send SMS messages. There's certain files it can't access, so they do sandboxing. Memory protection, so they basically had DEP on the device, and this was before. So the iPhone had DEP like a year before OS X had DEP, so it's actually ahead of the game. And they have a stronger version of DEP that you can't turn it off. So usually you can, there's no pages that are writable and executable, but you can set a page to be writable and then, throw some magic fairy dust and make it executable. But on iPhone, you can't do that, at least by design. Once a page is writable, you can never execute it. So that's another thing that they probably didn't put in for, to make exploitation harder. They probably put it in to protect, the App Store apps from doing crazy things, but it turns out that it makes it really hard to exploit. All right, so what about iPhone research? So iPhone 1.0 came out in June 2007, so it's been like, a little over 2 years now. And it was not a secure device when it came out. It was very, rushed out the door like most products. So everything ran as root. That's not good. There was no such thing as sandboxing, no ASLR, no depth, no code signing, so anything ran. It was hacked within a couple weeks by me and a couple other guys. And there were at least 3 public remote code exploits. And of course, since everything runs as root, these are remote root exploits. So pretty bad. They're all 3 bugs, as far as I know, were in accessible through mobile Safari. So they were all I had 2 JavaScript ones, I think, and then someone else found one in like TIFF, I think, some image format. So and the other interesting thing to show how easy this was. So now there's these jailbroken iPhones and all this stuff, right? So when I hacked into it, there was no such thing as a jailbroken phone. No one had done that yet. So I had no shell, nothing. I had no debugger. The way that I was able to do it, because there was so little security, was I could crash it, right? So I found the bug in Safari. So finding the bug was easy, and the same bug was in mobile Safari. But I could crash the thing, and then I could plug it into my computer, and I could get the Dr. Watson equivalent. So I could get the crash report off it. I could say, okay, yeah, this looks like a heap overflow. And so just by trial and error, I was able to get an actual exploit working. So if they would have had anything like ASLR and anything like depth, there's no way I could have done it. So it just goes to show you that those are actually good device or good tools to do in security. Okay, iPhone 2 came out last summer. That's when they added a lot of stuff. So in iPhone 1, there was no App Store. You couldn't download programs. They expected you to use everything over the web, but they were stupid. So it turns out people actually like to download programs and run them. So they included App Store. There was an SDK, with an emulator, and they added all sorts of stuff. So of course, all the stuff they added wasn't for security. It was to protect you. Well, security from App Store apps, really. So that's why they added the sandboxing. They added depth. They added code signing. Now everything runs as user mobile, except the things that can't. So there's lots of security. And I'll talk at the end about a way I figured out to get around this depth can never be turned off thing, which is, but they fixed that later. So anyway, iPhone 2 came out. Big change. It's very secure compared to iPhone 1. And the big thing that is proof in some sense that it's better, or maybe just me and the other guy who did iPhone research didn't look at it, is there's no known public remote code exploits for iPhone 2 or 3. And known, if you had one, you could get 10 grand, and no one had one. So it was more secure, put it that way. iPhone 3 came out this summer. They added some stuff like MMS. They fixed the depth bug I found. Still no ASLR. And basically, because it had depth, it was more secure than Leopard, but it's actually less secure than Snow Leopard, because Snow Leopard has at least some ASLR. Okay, so that's iPhone. iPhone 101. Let's move on to SMS. So you've already heard a lot about SMS, so I won't go into too much detail. But basically, SMS is just some extra stuff that extra bandwidth in the control channel that carriers can send data to your phone, and it's what, like when a phone is about to ring, the carrier sends some data over this extra bandwidth that says, hey phone, you got a call coming in, ring. So you can also send in message data of up to 140 bytes, which is 160 characters. And that's what, when you send text messages to your friends, hey, meet me at the party. This is what it is. It's an SMS. So SMS isn't the same thing as text messages. Text messages uses SMS. You can also deliver binary data besides just text, like, hey, what's going on? You can send in, for some phones, not the iPhone, you can actually do over-the-air programming. You can download ringtones with SMS, that sort of thing. But the point is that you can't turn off SMS. It's too important. Like, your phone won't ever ring if you turn off SMS. You won't ever be able to make a call if you turn off SMS. So it's essential for phones. So why did I decide to look at SMS? And actually, I wasn't the only one, right? So when BlueHat came out, there were like 3 talks, maybe 4, on SMS. And none of us had talked to each other about this. So it's like, why did all of a sudden all these researchers think SMS was important to look at? And this is at least the reason I looked at it. So all modern phones handle SMS. So, that's good. No way you can turn it off or firewall it. It has to be able to accept this data. I can send you an SMS to your phone and you don't have to do anything, right? So all the bugs that were in the earlier iPhone that I found were all like browser bugs. So you have to trick someone to go to a website or do some man in the middle or something. It's complicated, right? But it's easy to just send a text message. It can be in your pocket, and I can send you a text message, and your phone will process it. And so, this was like great. It's like, oh, this is just like when I started computer security back in 1990 when, everyone's port 135 was open on the internet. It was awesome. So it's the same way, and that's why I like it. The other thing is maybe I want to hack your computer and I know your IP address, but I don't know, or I know your name, but I don't know your IP address, right? So, I pick on you, right? You're in the front row, so I want to hack your computer. Well, I don't know your IP address, right? But I can probably find your phone number. I go, hey, who's that guy in the front row, man? He really looked like he had some questions. I want to follow up with him. Someone will give me his phone number, so I could hack him that way, right? So phone number is actually easier from a targeting perspective. And the other thing is, as I say in the end, so they actually do have these SMS firewall things you can buy for your phone, but they work at a higher level, and you can attack the actual low level SMS. So there's basically nothing they can do. It's a great attack vector. And none of these things really are going to change much either. So it's going to be a great, the port 135 on Windows being open was great for a while, but then, hey, people bought firewalls, and Windows Firewall existed, and, people bought routers to sit in front of their cable modems and stuff. So, but none of this stuff is really going to go away, at least for the near future. So it's still going to be a good attack vector. Okay, so how does this work on the device? There's actually two processors on your phone. One does what you would normally call the processor, so the web browsing and so forth. The other one's the modem, and that's the one that deals with the carrier. So the modem runs some specialized real-time operating system that I don't worry about. It's too low level for me. But the important thing is the two processors talk to each other over these logical serial lines using GSM app commands. So when I'm sitting here with my phone and an SMS comes, what happens is you get an at command result code. That's what shows up. And basically what it looks like is this. On the serial line between the two applications, you'll get these two lines. So it'll say a result code, and then a number, which is how much data to expect, and then this binary stuff, which is called a PDU. And the great thing about giving talks about mobile and doing mobile work is, everyone else is supposed to turn off their phone, but I can't turn off my phone because I have to use it for demos. So if my phone rings in the middle of a talk, you can't get mad at me. Okay, so what's this PDU thing I was talking about? I gave you an example in the last one. Let's break it out a little bit, because if we're going to fuzz this thing, we need to understand the fields. So just running through real quickly, this is what a PDU looks like. So this SMSC address is basically like your phone number. You'll get a link, so 7, a type 91, that means international, like an international form of a phone number, and then the actual phone number encoded in some way. So for those of you out there who like to look for bugs and do fuzzing, it's very typical to see this link type data. So whenever you see that, it's like, hey, this is something I want to fuzz. So then there's some other bytes that say like, hey, deliver means this is a text message coming down, or an SMS message coming to the phone as opposed to like leaving the phone. Then you get another phone number, which is who sent the message, and then you get some other fields that say things like, how is the data going to be encoded? Is it compressed? Is it 7-bit? Is it 8-bit? That sort of thing. Is it binary? Is it not? And then you'll get that long thing, SCTS, that's a timestamp, which no one really pays attention to, I guess. And then you get UDL, which is a user data length, so A in this case, and then you get the actual data. So that's what a text message looks like. So one of the reasons when I went into this, I said, hey, I told some of my friends, hey, I'm going to look at SMS vulnerabilities, right? I'm going to try to find some bugs. I'm like, no, you're never going to find anything. SMS is so simple, right? There's like no bugs. I send text, right? It turns out, so you even get in this, you're like, well, maybe there could be some bugs, right? There's like some links and types and stuff, and it gets worse. So that last thing I showed you was like, hey, meet me at the mall. That's the simplest kind of message there is, but there's way more complicated ones. So besides just sending text, you can also send data. And there, instead of just sending text in the UD field, so the user data field, you use what's called a user data header, UDH. So this is an example of what user data header looks like. So these bytes would show up in the data of a regular SMS message. And here I break it out again. So you get a header length, so in this case 5, and an IEI, which is an identifier, which is what kind of data this is. In this case, it's 0, and I'll talk more about IEIs. And then the data length, 3, and then the actual data. So in this case, 000301. Okay, so what does that stuff mean? So let's break that out and see what this means. So this is a concatenated message, concatenated 8-bit message. So concatenated messages, say I really want to talk a lot about going to the mall, right? So maybe I want to talk about going to the mall and what store and what time and whatever. So it's going to be more than 160 characters. So in that case, the phone can send a message longer than 160. It just sends it in more than one message, and your phone will reassemble it for you on your end. Sort of like TCP, right? So the way this works, that's an IDI of 0, means expected concatenated message. Then there's 3 bytes of data. So a reference number, which says like, different messages would have different reference numbers. So in case maybe you're getting 2 concatenated messages at the same time, you can keep it straight. Then the total number of messages to expect, so maybe you're sending 3, and in this case 1, so the first message. They count from 1, not 0. It's like the only time in computers that they do that for some reason. Okay. So what are some IEIs? These are the ones that the iPhone supports. I reverse engineered it. So 00 we talked about. 01 is voicemail. So whenever you get a voicemail, like it's like ding, on your iPhone if you have an iPhone. That's because you got SMS message with an IEI of 1. Applications can register for port numbers just like in TCP, except here they're port numbers for SMS, and those IEIs are 5. And then the very special port number on iPhones is 5499, which is visual voicemail. So visual voicemail sits on 5499. If it gets a message, it tries to process it. And this is what the kind of data that ends up to that port looks like, where I X'd out like things that I thought AT&T could find me and ruin my account or something. But it turns out now me and AT&T are friends, so they wouldn't do that to me. But at the time when I wrote this slide, we weren't friends. All right, so port 2948 is something called WAP push. Okay, and then there's this great program called PDU Spy. That same PDU I put in, it's just like a little Windows GUI that will break out all the fields for you. The bad thing about PDU Spy is almost every fuzz test case that I have that causes a crash, I'm like, oh, I'm going to put in PDU Spy, and it'll tell me what the difference is, right? It crashes PDU Spy too. Although PDU Spy actually handles it better. It like puts up like a dialogue. It doesn't actually crash. And it's like, oh, and it's in German. I can't read it. But, like an iPhone would actually crash. Okay, so now I want to actually do some fuzzing. Okay, so I use Sully, which is, so I need a way to generate test cases, generate PDUs that have problems and send them into the iPhone or other device. I should say I don't actually mention it in this talk, but I did other things besides iPhone and my BlueHat talk. I did Android, and I did Windows Mobile, which you might care about. So, and the way that I work is, I'm just doing this for fun, right? So I would turn on my fuzzer, and as soon as it found something that looked good, I would turn off my fuzzer, right? Because that's all I wanted is a bug I can talk about in my talk. So I found this great iPhone bug I'm going to talk about later. I found an Android bug. Android's written in Java, though, or the SMS implementation is in Java, so all I could do is like make a exception occur, and it would crash the thing, but I couldn't take it over. And then on Windows Mobile, I had this HTC Dream phone or something, and we turned on the fuzzer. It was like test case 1, 2, 3, 4, 5, 6, 7, killed it. So it was like we had like hundreds of thousands of test cases to try, and number 7 killed it, and it was a really, really serious bug too. But it turned out it wasn't in the Windows Mobile code. It was in TouchFlow, which is the little GUI that they throw on top. The HTC throws on top of Windows. So. Your guys' code survived at least 7 test cases, I can say that. So I'll turn it on someday when I'm bored and see if it can survive all 100,000. But it did better than TouchFlow, which only sent 7. So this was a really bad bug. So it turns out it was a format string bug. So if you sent like a %n, it would kill the phone, right? In a very exploitable way. And what's worse is my test case was gigantic, right? It was in some UDH field way down, like crazy. So I kept simplifying it and simplifying it and simplifying it to see like where the actual bug was. And I finally got down to, oh, you can just send a %n to your friend in your phone and it'll crash their TouchFlow. It was bad. And then, this is like props to you guys. So the thing that was worse was it would store this message, right? So it would crash the GUI, and then it would have the message stored. And so when you start back up the GUI, like you would reboot or something, it'd be like, okay, let me show you that last text message. Oh, and that killed me again. So the only way you could fix it was to go into the SMS application that was built into Windows, and it could actually display the %n. Surprise, you guys, fuzzed at least 1 test case. And you would remove the SMS message there, and then you could start up the TouchFlow and it would work again. So you guys, your code was the fix for their bug. Okay, so that's all I'm going to say about Windows and Android. But we found similar bugs in other phones. I just like the iPhone one because I actually wrote the exploit. Okay, so anyway, so I needed to generate these test cases. I used Sully, which is a fuzzing framework written in Python. It does lots of stuff. It generates test cases, it sends test cases, it monitors, it does postmortem analysis, but I only use it for test cases because I have code to do all the rest of that stuff. It uses a block-based approach like you might have heard talk about in fuzzing and spike and all that stuff. But basically it comes with a library full of things that have been found successful in the past. So for example, it had a %n in one of its fields. So it's like way better than Spike, and if you've heard of Peach, it's like Peach except no one maintains Sully anymore, and they still maintain Peach. And I just use Sully because that's what I learned on. Okay, so what does Sully look like? So you basically just have to describe what data looks like, and it'll generate a bunch of test cases for you. So remember back when I showed you what SMSC number looked like, it looked like this. And this is how I would describe in Python what this looks like to the fuzzer, and then the fuzzer could generate me a bunch of test cases. So you say, okay, well first there's a size. And the format is oct, which means it's supposed to look like 0 through 9 and A through F, right? That's how those PDUs look. I had to write that because no other protocol really uses this. And then you say, oh, and then the math is really divide by 2 because there's twice as many or something. Okay, and then so then there's a block. So this is the thing I'm supposed to find the length of. So then I have a byte, that's the type, and then I have a string that is supposed to be encoded. So that's what I call this 8-bit encoder. And that's it. So you just you give this much Python to Sully and you say go, and it'll generate like a ton of invalid SMSC numbers. Likewise, if you want to see what UDH looks like, it's just a little more complicated, and you can look, and there's different there's 2 sizes, right? There's UDHL and a IEDL, and you'll see those in there and so forth. But basically the point is you don't have to write too much Python to describe this, and then you can quickly get like millions of test cases. Yeah. But what do you do with the test cases, right? So I could literally just send them all like 100,000 or million from one phone to another, but I don't have an unlimited SMS plan, and even if I did, eventually they are going to kick me off. The other thing is I don't want the telcos to watch me fuzz, because then they get all my test cases. And this is my own stuff, so I don't want them to know what I'm up to. And the other thing is their equipment is handling these text messages going from my phone to the other phone, and eventually I'm fuzzing their stuff too, and I don't want to fuzz their stuff because I don't want to go to jail. So the other thing you could so I don't want to send it over the air. I could build my own radio, but that sounds way too hard to me. I just I like writing Python. That's about it. So. What else can I do? Okay, well I could actually, inject it into the actual process, which is, I was talking to some mobile guys here, and that's what you guys, I guess, do. But for me, that's not good because I want to do iPhone, Android, and I want to do Windows Mobile. So it would be too dependent on the firmware. And so I just did SMS injection between the 2 processors. So I basically do a man in the middle between the application processor and the modem. And so at least with GSM, they have a serial line. They do these @ commands, and it's very easy to just to do that. So I basically do library preloading, and when it tries to open up or read or write to this virtual serial line, I just get in the middle of that, and I also open a TCP port. And so I'll if regular SMS messages are going on, I just ferry those back and forth. And when it gets something on the TCP port, I put that in, and it can't tell the difference that this came from me versus the real network. Like I said, so the great thing is I can hammer, as fast as I can send TCP packets, I can send SMS messages. Doesn't cost any money. Don't have to buy any equipment. I don't have to know jack about radios or how they work. The receiving process can't tell that they didn't come over the actual radio. For the most part, the telco company doesn't know I'm up to anything. And the one thing you have to watch out for, though, is if you find a crash doing this, it's not really legitimate until I've actually sent it over the network. So sometimes we would find crashes that would work this way when I inject it. When I actually try to send it over the real network to another phone, the AT&T or somebody would have filtered it, and so it never got there. So you have to verify everything still works. And then here's the actual code you can do to set up the library preloading. And then the Python you need at this point to just send the PDU is real easy. You just send it. Done. Okay, so that's everything you need to know up to this point. Now let's talk about the bug I found and how I exploited it, and you'll see how the work you had to do this. So, like I said, the first thing I had to do was make sure that this bug was legit, that you could send it over the network, and you could. It turns out almost all of the ones we found you could send over the network, so the carriers don't do a whole lot of filtering. So then we built a small application that would actually, by sending GSM MAC commands, would send the thing. And it turns out that the interesting thing was different carriers filtered different things. So there were sometimes, Colin was in Germany, sometimes his carrier would allow him to send one to me, but like I couldn't send it to him because AT&T would filter it or something. So it's sort of interesting. You had to try different things. It turned out the one that was really serious, everyone let go. And here's what it is. So this is what the crash looked like. So you're fuzzing, and then you start to get things like this, and you're like, cool, I found something. And when I talked to BlueHat, this was when 3.0 was out. It hadn't been fixed. But the next day, they fixed it. I had reported it like a month earlier, like a good guy. And so they fixed it the next day, and that's why 3.01 was released, was because of this bug I'm about to show you. Oh yeah, so this is my Terminator quote. Like every talk I give has Terminator quote in it. So this white thing is actually the bug. So the bug, in its most simple form, is represented by this. 04, 00, 03, and then any 2 bytes you want. So that's how simple this bug is, but it's pretty bad. And the point of the quote is that, okay, so if I can send you an SMS message and take over your phone, like this is like, Blaster for phones, right? So then I read your contacts, and since iPhone people are all a bunch of Apple geeks, all their friends are probably Apple geeks too. So I can just send out SMS messages to all the phone numbers they know, and then all the phone numbers they know, and so you can basically take over all the iPhones in the world in a couple hours. So it's pretty cool. All right, unless you're Apple. So let's take a look at this bug. So the bug is there's a function that I call for them, read next byte. And what it does is it's reading bytes off of the SMS message, the PDU that you sent it. And it returns 1 byte, the next byte, obviously, unless there's an error. So if maybe it runs out of bytes to read, instead of returning the next byte, since there is no next byte, it returns -1 to indicate an error. So if you look through, it says, okay, remember those 3 bytes for concatenated messages? It reads the reference number, the total number of messages, and then what message number this is. So that's exactly what this code does. What could go wrong, right? Well, it turns out that the bad thing is, if you don't send in enough data, get next byte starts returning -1, but they never actually check that this error could occur. And so it starts thinking that these -1s are valid numbers. And so you can make this message number be -1, or you can make the total number of messages be -1. So there's lots of weird things that can happen. Or this is just the field I happened to pick, which was concatenated messages. But you can do this for any of the fields. All right, so this is bad that they do this. And the reason is the following. So this is actually, on the bottom, is a PDU that you could send to someone who hasn't updated their iPhone, and I think it crashes their phone. So actually, so it crashes Comm Center, which is the process that handles SMS and their phone. So it'll knock their phone off the network for, and for as long as it takes the process to restart, which is like 5 seconds. And here's another funny story. Well, funny for me. So at BlueHat, I was going to, well, I won't say that part. So at BlueHat, I wanted to do a demo, right, to show that this was legit. And so I found someone at the last second who worked for some carrier somewhere. And he said, oh, you can use my phone. So we started sending so the idea was, okay, well, I can knock you off the network for 5 seconds with an SMS message. What happens if I send one every 5 seconds, right? So I started sending him the SMS messages every 5 seconds or whatever it was. And then, like, as a demo, I tried calling his phone, and sure enough, like, he couldn't pick it up, right? It just went straight to voicemail. It's like, oh, this is a great demo, okay, whatever. So then, of course, I turned the thing off at the end of the talk to put him back on the network. And one of the great things about SMS messages is that if you're not on the network and someone sends you an SMS message, the carrier queues those up for you. So the next time you turn on your phone, it's like, oh, hey, while you were gone, here's a couple of text messages that someone sent you. So I didn't know anything was wrong, but like 3 hours later, he comes up to Colin, the guy I gave the talk with. He's like, hey, Colin, when are you guys going to turn off the attack? And I was like, oops. So apparently, like, we were sending them slightly faster than his phone was restarting, and so the AT&T or whoever had queued up like thousands of these malicious SMS messages, and it just kept sending and sending and sending. So he couldn't be on the network for hours, and eventually, they all got there, and everything was great, but it was pretty funny. Anyway, so what happens with this bug? So if you can read this code, what happens I think I have it on the next slide actually. So anytime you get a new concatenated message, say of size, say you say, oh, there's going to be 10, expect 10 SMSs for this, concatenated message. So it allocates an array of 10 pointers to C++ strings in that case, however many you say there's going to be. And then whenever a new one comes in, or whenever the next one comes in, and you say, okay, here's the next one, it's number 4, right? The first thing it does is it checks to make sure that it's like, oh, did I already get one that's number 4? I.e., is the pointer to a null C++ string, or is it to like one that I already have? And so that's how it knows whether you've already gotten this message, and if you've already gotten it, it just throws it out. Otherwise, it uses this array, and it's great logic. It says, oh, if you send me a 0, I know there's nothing, there's something wrong because I only expect them to be, starting at 1. If you send in one that's too big, it's like, no, you're trying to do something evil. You're saying too big, it kicks out. The problem is if you send in one without enough data, then you get this number of -1 because that function, is indicating there's an error. And then it's like, oh, the -1 spot in the array, cool, I'll go there. And then, bad things happen. So that's the bug, is you can access a pointer before an actual allocated array on the heap. All right, so then what happens? Like I said, so what's it do with this value that isn't really in your array that it's looking at? And what it does is it says, I'd like to compare this to see if it's a null string. And it's not a C string, so it's a C++ string. It's a structure. So what it does is it compares, and in the structure there's things like links, and the actual data, of course, and like reference numbers and stuff like that. And so it compares it to see if it's the null string, which means it has length 0. Okay, so and we want to do things as an attacker, right? So we want this thing to end up pointing to something that it's going to think is a null string, so that it'll keep processing. Because otherwise, I said, it just throws it away, and we don't want it to do that. So the way you have to do that is you have to have a length of 0. And so that means wherever you're pointing this thing to, so it's going to be just some random value on the heap. But if you suppose you have control of that, you want to point it at something that has a 0 somewhere, a 0 D word. And that way when it goes to do this compare, it'll say, oh yeah, it's a null C++ string, let's keep going. All right, so then the next thing it does, once it says, okay, this is a null string, now what am I going to do with this data that someone just sent me? It tries to assign that data to that C++ string. And the way it does that is first it does this function called exchange and add, which basically turns out to do, so the first thing it's trying to do is get rid of the null C++ string and basically replace it with a C++ string of the data that you've sent it. So the first thing it does is exchange and add, which basically does a decrement of the reference counter of the string. And then it calls destroy, which is like free. So that's what it does. All right, and this is what it is in words, what I just said. So you want to replace the old string with the new string. So what it does is it adjusts the links, which isn't important. And then it wants to get rid of the old string, which it does by decrementing a value from this structure, and then it frees the buffer. And again, remember, this is going to be some value that it shouldn't be messing with. So, so what do we need to do? We need to make sure that we control this value that happens to lay in the heap right before our buffer. And then we want to make sure that it points at something that has a 0D word. And if all those things happen, then what we get out of it is we can decrement something and we can free something. And it turns out that either of those two things is enough to completely take over the process in theory. But the problem is, like if I'm attacking IE or Safari or something, I have a lot of control. I can run JavaScript, I can have it download images and all sorts of crazy stuff, right? But here, all I can do is send SMS messages, right? So the question is, just by sending SMS messages, is that enough that I can arrange things to make all these things happen? And I wouldn't be here if I couldn't. So yes, this is the answer. So how do you do it? Well, let's think more about concatenated messages, because that's the key to everything here. Every time there's a new reference number, I already explained there's this array of strings that's allocated. That's fine. So we already talked about that. And also, when new data comes in, obviously that string has to be stored somewhere. So that's another place where things are allocated. And finally, when the concatenated message is done, so maybe you have like 7 of these messages, well, it wants to show it to you on your phone. So it concatenates them all together into one big string, shows it to you, and then frees it. So that's what else is done. So these are the 3 things we can do. We can allocate buffers of size 144. That's the C++ pointer things. And then we can, oh wait, that's the second thing. So first we can, this is the first bullet is the data from each of the messages. The second one is the array of pointers to strings. Each of those guys we control when they're allocated and when they're freed, because if we don't ever complete the message, it never actually frees them. And then the last thing is we can create one big old monster long string, but it doesn't stick around for long. That's all we have at our disposal, but that's enough to completely massage the heap to do exactly what we want. All right, so actually kind of running out of time, so I'll just go sort of a little quick, and if you can't get it, then catch me tonight or something, and I'll explain to you, or watch my longer talk. So the question is, what do I want to decrement, right? And it turns out that you need to know a little bit about the way the heap works on OS X. And the way it does it is, for different size buffers, it keeps a list of all the freed pointers. And then whenever you go to malloc something, it grabs something, if there's something already of that size in the free pointer, it just gives you that. It just recycles it. And if there isn't one exactly that size, it takes a bigger one, if there is one, and gives you, that portion of the big one that you asked for, and then it splits it, and the little one it puts back on the freed pointer list in a littler slot. That's all you need to know as far as memory management goes. Okay, so then what can you start to do as far as manipulating the way the heap's laid out just by saying SMS messages? Well, one thing you can do, and I already sort of alluded to this, is you could send a different, like a long concatenated message. Say you're like, okay, expect a concatenated message of 100 SMSs. But if you only send 99 of them, they'll all be in memory, but it can't free them because it wants to concatenate them at the end, and it hasn't ever gotten the 100th message. So in that case, each of these messages can have 140 bytes, and then you end up with, 0x90 byte buffer, and you can send up to 254 messages, and each one of those, and then there's different reference numbers too, so there's 255 different possibilities there too. So you end up with filling up 9 megabytes of the heap. You can massage out your data. And if you use 16-bit reference numbers, you can get 2 gigabytes of the heap. So you can fill a lot of the heap with this stuff. So you can do a heap spray, even though you can only send 140 bytes at once. And like the last bullet says, the best thing is you can be doing this, and the user never knows it, because until you complete a concatenated message, it never gets displayed. So they have no idea this is going on. And this is what it looks like in a debugger. So I'm sending in 3 different messages. This one's the first one, the second one, the third one. And then in memory, I see my stuff laid out nicely. All right. And then also you can do other more complicated things, like instead of just trying to lay it all out right in a row, you can try to create holes, which is going to be important because we want to control things before the buffer, right? And so the only way you can do that is to have something already there and have your thing end up right after it. So the way you do that is you can do like reference 1, this one, reference 2, this one, reference 1, this 2. So you end up with 2 reference numbers and you intertwine them, and then you complete one of them. And so one of them gets freed, but they're every other buffer. And so then you end up with all these holes in the heap. And this is what it looks like when I start to do the attack. So the thing that's in blue is the buffer of C++ pointers, and that's the thing that I can allocate, or I can access before, because it does a -1. That's what it's pointing to -2. And the way I did that was I created a bunch of holes, and then when I did allocate the C++ strings buffer, it ended up in one of those holes, and so I controlled the thing right in front of it. And so here, when it tries to do the compare, it accesses that 414141 pointer thinking it's a C++ string, and it dies. So I'm on the right track. All right, so I can now, if I would have laid out my data better, I could have started to do things like decrementing and freeing things. But what do I want to decrement? Well, one thing you can do is look at a pointer on the freed list. So if I could decrement, if there was a pointer on the free list and I controlled the data before that pointer, I can start decrementing that thing, and then it's no longer actually pointing to like heap metadata anymore. Now it's pointing to my data. And then when it does the unlinking, this is like the old attack from like 5 years ago on heaps, you get a write for primitive out of it. So that's what I do. And the other advantage is that the freed list in Mac OS X is always at the same exact address. There's no randomization. So I know right where to look. All right, so this is everything that I want to do to take control. It's a lot, right? And the question is, is it possible? So I want to make sure I control the data right before an array of C++ strings, which I'm going to underflow. I want to make sure I have data right before a pointer on the freed list, so that when I decrement it, it points into my stuff. Then I want to actually do the decrementing of it, and so it points into my stuff. And then I want to do an allocation so that it gets unlinked. And then I want to, that'll give me a write for, so I want to write for somewhere important, and then I want to call a function that's going to get that thing that I wrote. So it's you know, a lot of work here. But I can do it. So, and this is exactly the way I do it. So the first thing is do a small message that I don't complete, and then I do like a long message. I create the holes, so I create n holes in the heap using the thing I talked about earlier. And this also has the benefit of clearing out the free list because I'm doing lots of allocations. So then, and then the whole point of this like small message to start with is this is the guy I'm going to decrement on the free list. So then I want to put that on the free list, so I finish that one out. So then what I got is a lot of holes, and I start sending in these guys that are doing decrements. So they land in my hole, I access -2, and it does a decrement of this pointer on the free list. I do that 16 times, and all of a sudden, if I really controlled the data before that pointer, then bad things are going to happen very soon. And then all I do is I make an allocation, and things are great. All right, so what kind of data am I sending in? If I want to just show you what I'm up to, I can do that. So the last thing that's highlighted is the actual address of the thing on where the pointer on the free list is. And then I just do some tricks. That stuff before it will become the heap metadata, the fake heap metadata. And likewise, on the bottom, I just put in something more realistic. I put in the address of where pthread mutex lock, which happens to be a function that it gets called. So this is what it looks like, the whole attack. So this thing in the middle is this free list that I'm telling you about. The one that's highlighted is one that's been decremented by 16 times. Then on the bottom, you can see this is where that buffer is. So you look where it used to be. On the bottom row is what heap metadata should look like. But since I decremented it 16 times, it's actually pointing to the data I control, which is the fake heap metadata. Then you can see where it crashes, which is in malloc. It was trying to do the unlinking, and it actually did store R2 into R3, so it did the write Babe Cafe into Dead Beef thing. So you can see I can actually do the write. So at that point, it's easy, right? Switch out Babe Cafe for something legit, and you're good. So here, at this time I crashed it, and it's actually, the program counter is pointing to whatever I want. And like I said, I spent the first couple minutes talking about the security model of iPhone. It turns out this breaks like every single thing. So it doesn't require user interaction. Everything runs as mobile, right? Well, not everything. Comm Center runs as root. So here you get root, and it's not sandbox. So even Safari is sandbox, but not this thing. So unsandbox, remote root, and there's nothing you can do about it. It's pretty awesome. All right, so what happened? And all the attack is 519 SMSs. You only see one as an end user. And if you mess up, you can just try it again, because when you reboot, if you crash the thing, it starts over and it's a clean slate. So you just keep trying until you own them. Okay, let's see. I got like 5 minutes to finish up. Like, it's only a couple slides. It's basically a demo. So iPhone 2, any page that's writable was not ever going to become executable. But then I started thinking, like, well, how the heck did debuggers work, right? That's what debuggers do. And so it turned out that if you could take a library, you could override it, basically. And you could do that using return-oriented programming, for example. All right, so what does this bug mean? Besides, like, I can run shellcode, which is cool. They're probably more concerned that App Store code can update itself, like, i.e. do things that Apple didn't think it was going to be able to do. The dynamic linker can be changed on the fly, since I can change libraries. And what does the dynamic linker do? It makes sure that only signed libraries get loaded. Well, I can patch it so it loads things that aren't signed. All right, so one thing I want to load is Meterpreter. So Meterpreter is a payload that was originally for Windows. It's like a shell, but better, because not only is it a shell, but you can upload, download files, do all sorts of other stuff. I ported it to OS X last year, so then it was pretty easy to port to iPhone. And the best thing is, so there's no SH on a phone. I can't get a shell on a phone. But with Meterpreter, it's like I have a shell. So it's a shell on a system with no shell. Okay, demo. I'll try to do this quickly. So this is a phone. It hasn't been updated since 2.2.1. It's not jailbroken. It's not a development phone. The only thing I did was I did ad hoc distribution because I had to get a vulnerable app on the phone. So let's see if this works. So I'm going to try to take advantage of this, of a vulnerable program I put on there and upload Meterpreter. And let's see here. So here is the box that's going to be running Metasploit. Let's see. And then I have to get to it real quick. It'll take like 1 second here. You guys aren't man in the middle-ing me, are you? Come on, come on. Yeah, if I can't get the thing working in like 2 minutes, we'll just quit because it's not that great at demo. But okay, so here is so I have different ones for different versions of iPhone. And let me just put in the old IP address here. Ah, I lost my IP address. Son of a biscuit. Let's see. Yeah, we'll give it like 1 second here to get an IP address. So I'm on my own. You can join my network. It's called Charlie Miller's Computer. You'll find it on your wireless right now. Okay, let's see. You can actually attack my iPhone if you want. 82.91. Now you all know my iPhone's IP address. Okay, so it's running, and now quickly I'm going to start the vulnerable application, which says hello world, of all things. Okay, so right now it's sitting there doing its Ruby thing. It's sending the payload. Let's see. Can you guys see that? Oh, I'll make it bigger here. Okay, so now this system has no shell because there's no bin sh, but look, I like have a shell. And then so I can do things. I can look at files. I can ls. I can do lots of other things. I can do ps. And if you know like lots about iPhone, you can tell that this isn't like a rig demo too much because like on debug phones there's like debug processes running, but here there is none. And then I can say like, so you can see hello world's running. I can say get PID, so you can see I'm actually inside hello world, which isn't surprising. What are some of the other things I can do here? There's another like get UID or something. So I'm user mobile, which isn't surprising. And then you can also, it's real easy in Interpreter to add in code specific for this. So like you can write phone or code to do stuff specifically for a phone. So like I wrote one called vibrate, which makes my phone vibrate. Let me see if it works. Did you hear that? So you can do that. I have one that sends SMS messages, but this particular app is in a sandbox and can't do that. But if I was in like say, some like say comm center, then I could just type send SMS and it'll do it. I have a send SMS and I have a call to dial a phone number too. So anyway, this is a shell on a system with no shell. Okay. Let me get back to the slides here. Okay. So they fixed this bug that lets me disable the DEP. As far as I know, no one knows how to get generic shellcode running on iPhone 3. But there's no ASLR, so you can always do return-oriented programming, to your heart's content. So conclusion, SMS bugs are very bad. Make sure you guys don't have any. You might not think you can do heap manipulation with just 140 bytes at a time, but you can, but it's very hard. I should say my 519 SMS's exploit, it didn't work every time. So it was like 1 in 3 or 4 times maybe, and each one took like 7 minutes because I would only send one SMS a minute, or I mean a second. So it would basically, like if I wanted to own you, I would have to stay up all, set it to go to bed and wake up in the morning, and I would have a shell on your phone or something. So it's not even heap manipulation over SMS is not super reliable, but you can do it. You can do fuzzing over a local network. Against 221, you can get a root-owned interpreter shell, all via SMS. And iPhone's getting better, but it still doesn't have ASLR. That's it. Thanks.